Hello, good morning. Today we are going to discuss about algebraic structures. So, in this section, we are going to define semi-groups, monoid, and groups, and the concept of Lagrange's theorem will be addressed in our next class or next session. So, here formally, we start with the concept of binary operator. A binary operator is a function defined from across A to A. Or in other words, it's an operation in which take two input from the same set and give uh, an element from A as the output. Such a operation is known as a binary operation. So let us have some examples. If we consider the set of all real numbers, then the addition defined on set of all real numbers is a binary operation. We have two input A and B, and the output plus B is also a real number. If we define the addition on set of all complex numbers, this is also a binary operation. And if we consider the set of all 2 by 2 real matrices and consider the addition of 2 by 2 real matrices, then the sum of 2 by 2 square matrix is again 2 by 2 square matrix, and that's also an example of a binary operation. Similarly, we can extend this to n by n matrices also, and if we define multiplication, division, etc. on set of all real numbers and complex numbers, that become a binary operator, except if we consider the set of all real numbers together with the division, then there is a problem with the element 0. We cannot define the division by 0. So if we are dealing with the binary operation of division, then it's better to consider the set of all real numbers except 0 together with the binary operation of division. And same is the case with complex numbers. And similarly, we can add two matrices, R2 n-tuples, R2 ordered pairs, etc. They are all binary operations. Now, there are operations which are not binary. Some examples, if we consider the operation of taking A inverse or A transpose or adjoint of A, they are not binary operations because it has only one input and one output, and the input and the output are elements of the underlying set, and therefore these kind of operations are known as unitary operations, not binary operations. And in some cases, say if we consider two vectors, say v1 and v2 are two vectors, then v1 plus v2 is again a vector, and therefore it's a binary operation. But if we multiply v1 and v2, so in the case of vectors, we have two kinds of multiplications. One is v1 cross v2, and the other one is v1 dot v2. When we take this v1 cross v2, the output is a vector, something like say v3, and when we take the dot product, the output is a scalar, something like a, and it's an element of set of all real numbers. So in the first case, when we consider the cross product, it is a binary operation, and in the second case, it is not the kind of operations which we are dealing here. The output is not belongs to the set of all vectors. And same is the case with the scalar product or scalar multiplication of a vector. There we have two inputs, but they are not from the same set. So that's also again not come under our discussions. So that's the concept of binary operator. And the common binary operators are addition, multiplication, etc. defined on set of all real numbers, complex numbers, matrices, vectors, etc. Now here we are going through a number of properties of binary operations. First one is closure property. So if you have an underlying set capital A, and if you take two elements from A, say small a and small b, then star b a binary operator defined on the set A, then a star b. If a star b is an element of A itself, if A star B belongs to A, then the operator star is to be closed, or A together with star, that pair said to have the closure property, or star is to be closed. Anyway, if we take two real numbers and add them, then it belongs to the real number, so it has the closure property. So that's the interpretation. Then there are cases in which we don't have this closure property. For example, if you take the set of all positive integers and consider the subtraction operator minus, or set of all positive integers with the division, say, division. Then, if you take two real numbers, say 3 and 2, then 3 by 2 is not an element of Z plus. So, it's not a not have the closure property. So, there are situations in which we have closure property, and situations in which we don't have closure property. And now, the second property is associative property. Is very straightforward. A star B star C is equal to A star B star C, and it is a common property among most of the binary operations. Now, the third property is existence of identity element. Uh, that's there exists a particular element, usually denoted by E, belongs to the underlying set A, such that A star E is equal to E star A is equal to A. For all elements of A, we have this particular identity or particular property. For all A belongs to capital A. So for example, if you consider the set of all real numbers together with addition, then 0 is the identity element, because for any real number, x plus 0 is equal to 0 plus x is equal to x. So 0 is the identity element. If you consider the set of all 2 by 2 matrices under addition, then the identity element is a matrix 2 by 2 matrix with all elements are equal to 0. So in for different operations or binary operations, we have different identity elements, and that identity element should belongs to the underlying set. Then we state that the binary operator has an identity element, or there exists an identity element in this in the set A. And now, existence of inverse. So if we take an arbitrary element from the underlying set, then there exists an element, a particular element in capital A, which is usually denoted by A inverse, in such a way that A inverse star A is equal to the identity element, and that's equal to A star A inverse. If such an element exists, then it is known as the inverse of A. And if the inverse exists for all elements in A, then we say that the binary operator has an inverse in the set. Anyhow, if you consider the same R plus set of all real numbers together with addition, and if you take an element x belongs to R, then we are looking for the inverse of x. So we are looking for an element such that x plus something equal to 0, and that means that something is equal to minus x. So minus x is the inverse of x in R under addition. But if the operator is multiplication, then we cannot consider the set of all real numbers. We have to eliminate 0. So usually when we eliminate 0, the obtained set is usually denoted by r star. And if we consider r star under multiplication, then a star or a into something is equal to the multiplicative identity. The multiplicative identity is 1, and obviously this something is nothing but 1 by a, and 1 by a is obviously an element of R, because a is not equal to 0. 0 is not an element of R star, so a is not equal to 0, so 1 by a belongs to R, and therefore the inverse of each and every a, arbitrary a, belongs to R exists, and therefore is it said to have an inverse. Then when we consider the 2 by 2 matrices, not every matrix of the form A, B, C, D process an inverse under multiplication. Under addition, we have the inverse of A, B, C, D as minus A minus B minus C minus D, and in such a way that A, B, C, D plus minus A minus B minus C minus D is equal to 0. So that's the inverse under addition. But under multiplication, not every matrix process a inverse. Only matrices with non-zero determinant will process an inverse. Now, the next property is commutative property. Obviously, A star B is equal to B star A for all values of all A and B belongs to A. Then the operator is said to have commutative property. And remember one thing, many of the binary operators have commutative property, but there are some operators which do not have commutative properties, like the division a by b and b by a, or a divided by b and b divided by a are not the same. So a into b is equal to b into a, so that's how commutative property. But a by b not equal to b by a, so it do not have commutative property. And in the case of real numbers and complex numbers, a plus b is equal to b plus a, but a minus b not equal to b minus a. So the first one has commutative property, and the second one do not have a commutative property. And if we define some operations like so a star b is defined as a plus b minus ab, then we have to check whether it have commutative property or not. A star b is equal to a plus b minus ab, and b star a is equal to b plus a minus ba, and that is equal to a plus b minus ab, and that's equal to a star b. So it's how that this particular operation have commutative property. And if you consider the multiplication of two vectors, cross product of two vectors, then it do not process the commutative property, because a cross b is not equal to b cross a. And in general, matrix multiplication is not commutative. A into b is not is equal to b into a for say n by n matrices. So there are operations these are some operations which are not commutative. Now we are going to define some particular type of algebraic structures. First we start with the definition of semigroup. Here we have a non-empty set capital S. Capital S is a non-empty set, and star is a binary operator defined on S. Then this S star is said to be a semi-group if S star is closed under the binary operation. That is, if we take two elements from S, then A and B, then A star B belongs to S itself. Then the second condition, the binary operation star is associative. If we have these two properties, then S star is said to be a semi-group. So let's have some examples. If we consider the set of all natural numbers together with addition, set of all natural numbers together with addition, then it will have the two properties. Natural numbers, if you add two natural numbers, then the sum is also a natural number, so it is closed. Then it is associative. Under addition, it is associative. So n plus is a semi-group. Then second one, the binary operation, a star, where a is the set of all positive integers greater than 13. So a star, we can consider the addition itself or usual multiplication, both will work. So let us consider the multiplication here. Then a and multiplication. Then if you take any two elements from A, they are two positive integers greater than 13, and if you multiply them, what we get is also a positive integer which is greater than 13. Therefore, it is closed under the multiplication, and the binary operation multiplication is commutative also. So binary operations star is associative also, and therefore it's a semi-group. So these two are semi-groups. Now, say one more thing. If we say the set of all natural numbers, usually we refer to 1, 2, 3, 4, 5, 6, etc. up to infinity. And in some cases, our reference is to 0, 1, 2, 3, etc. the whole numbers. So usually in our discussion, we follow the method n is equal to 1, 2, 3 up to infinity, and w is equal to 0, 1, 2, 3 up to infinity. And if we consider the set of all integers, we use z is equal to 0 plus or minus 1 plus or minus 2, etc. And this n is also denoted by z plus, the positive integers. And so that's our representation. Anyhow, the second structure, algebraic structure, is that of monoid. So for a monoid, M is said to be a monoid when the binary operation defined is closed, and the operation is associative, and there exists an identity element in M. So in addition to the properties of or the axioms of a semi-group, we have one more axiom which says there exists an identity element in M. So what if we look at the previous examples? Then n plus set of all positive integers together with addition. The identity element of addition is 0, and 0 is not an element of n. 0 does not belong to n. So n plus is not a monoid. And if you consider the set of all integers which are greater than 13, and under multiplication it forms a semi-group. But if you are looking for an identity element of multiplication, the identity element of multiplication is an element such that a into the identity element is equal to a, which means since it is multiplication, is e equal to 1. And 1 does not belong to the set A, because we consider the set of all elements which are greater than 13. 1 does not belong to that, and therefore A star is also not a monoid. Then can we find some examples of monoids? So here, set of all real numbers together with addition is a monoid, because it has the closure property. If you take any two real numbers, its sum is a real number, addition is associative, then there exists an identity element which is under addition it is 0. 0 belongs to R, and in such a way that x plus 0 is equal to 0 plus x is equal to x. So that's a example of a monoid. And second one, the set of all 2 by 2 matrices under multiplication. So if you take any 2 by 2 matrices under addition, it is already a monoid. But under multiplication, what happens? Under multiplication, if you take two by two matrices, say A and B are two by two matrices, is product A cross B, uh, another 2 by 2 matrix, and it belongs to R raised to 2 by 2. So it is closed. It's associative. Matrix multiplication is associative, and it has an inverse for some elements. Anyhow, there's an identity element under multiplication, which is nothing but 1001. 1001 will work as an identity element under matrix multiplication, and usually it is denoted by I 2 by 2. Okay, so this is the identity element here, and therefore R raised to 2 by 2 under matrix multiplication is a monoid. And one more thing, this is an example for a monoid which is not associative or commutative, not associative, commutative. Yes, cross B is not equal to B cross A. So this one is an example for monoid which is not commutative. It's not commutative. Now another example, Z plus set of all positive integers under addition. Set of all positive integers under addition is not a monoid, but if we include 0 to it, that is if we consider the set of all whole numbers W, then it become, if we consider set of all non-negative integers, then it become a monoid, because 0 is there, and it is closed under addition and associative under addition, and the identity element is there, so it becomes monoid. And now the next stage of development is into the concept of group. A binary non-empty set G together with a binary operation star is said to be a group. It's not semi-group, it is group, said to be a group if G is closed under the binary operation. Same axioms which is seen for monoids. The binary operation star is associative. There exists an identity element in G, and every element of G has an inverse in G. That's the new one. All other are already present in monoid. So if there exists an inverse in G for all elements of the group or of the underlying set G, then it is said to be a group. So if you consider the set of all complex numbers together with addition, then for any if you take any two complex numbers, then its sum is a complex number. If you take any three complex numbers, then we can simply prove that they are associative. Then if we consider the set of all complex numbers, then uh, under addition 0 plus I into 0 is a complex number, and this is usually denoted by 0, and for any complex number z plus 0 is equal to 0 plus z is equal to z. So there exists an identity element. So by the things which we mentioned so far, we can claim that C plus is a monoid. But moreover, if we take a complex number x plus iy, then there exists a complex number in C such that x plus iy plus z is equal to the identity element 0, and that z is equal to minus x plus I into minus y, or in simple words it is minus x minus iy, and that's a complex number, and we know that x plus iy plus minus x plus minus iy is equal to 0. So this minus x minus iy is the inverse of x plus iy. So the inverse of x plus iy is minus x minus I into y. And this exists for all complex numbers, and therefore set of all complex numbers together with addition is a group. And now set of all n by n matrices are to the power n by n under the matrix multiplication. Under matrix addition, okay, let's start with addition. Under addition, it will form a group because sum of two n by n matrices is an n by n matrix. The addition of n by n matrices is an associative operation. If you consider the n by n matrix for which all the entries are zeros, then it will work as an identity element. And for inverse, if Aij is the n by n matrix, then minus Aij will work as the inverse of the matrix. So that is, by all this we can claim that under addition R is n by n form a group. Now what if we consider the case of multiplication defined on all these sets? So let's start with the set of all real numbers. If you consider the set of all real numbers under multiplication, okay, under multiplication there is an obvious problem with 0, so we just eliminate 0 and define the multiplication operator on R star. Then if you take any non-zero real number, say a and b, its product is also a real number, so closure property is there. If you take three real numbers a, b and c, then the order of multiplication is immaterial, so it is associative. Then third property, if we have a real number a, then there is a non-zero real number 1 such that a into 1 is equal to 1 into a is equal to a. So 1 is the identity element. Then for if we have a real number a, then a into a inverse is equal to 1 means a inverse is equal to 1 by a, and this 1 by a belongs to R star because a is not equal to 0, 1 by a is a real number and non-zero real number, and that belongs to R star. Therefore it is again for this possible for all real numbers, for all a belongs to R. The third one is possible for all a belongs to R, and therefore we have inverse for all elements, and thus it is a group. In a similar way, we can prove that the set of all complex numbers except 0 is a group, and the identity element is obviously 1, and if a plus ib is a complex number, we can find the inverse of that complex number a plus ib, or if z is a complex number r e raised by theta, then we can find the inverse as 1 by z is equal to 1 by r e raised by minus I theta. So for every complex number which is not equal to 0, we can find out the inverse, and therefore c to the with multiplication is also a together with multiplication it's also a group. And when we consider the set of n by n matrices under addition, it will form a group. And what happens under multiplication? R raised to 2 by n by n be the set of all n by n real matrices, and together with multiplication. Now if you take two n by n matrices, its product is an n by n matrix, so it is closed. Then associative, and the identity element of matrix multiplication, there exists an identity element 1 0 0 0 0 1 0 0 0 0 0 0 1 etc. That identity element belongs to R raised n by n, and therefore the identity element exists. And when we look for the inverse, there is a problem. Not all n by n matrices process an inverse. Those matrices for which determinant not equal to 0 will process an inverse in R raised n by n. So there are elements in R raised n by n, which has an inverse, but at the same time, there are elements in R raised n by n which do not process any inverse, and therefore it is not a group. And before moving into our next definition, let us consider one more important type of group. If we consider the set of uh, cube roots of unity, usually denoted by 1 omega and omega square. So we have three cube roots of unity. One cube root is 1, and other two are complex cube roots. They are omega and omega square. And if we consider these cube roots of unity under multiplication, complex multiplication, then that will form a group. And except from other than or this particular group has a peculiarity. It has only a finite number of elements, and therefore this group can be represented using a tabular form. So if you write like this, 1 omega omega square, 1 omega omega square, then 1 into 1 is 1, 1 into 1 is 1, uh, 1 into omega is omega, is omega square, and omega square. Then omega into omega is omega square. Omega into omega square is omega cube, and omega is the cube root of unity, so omega cube is 1. Then omega square into omega is again 1. Then omega square into omega square is omega raised to 4. Omega raised to 4 is omega cube into omega. Omega cube is 1, so it is omega. So if we have a group which contains only a finite number of elements, then we can represent the group structure using a table. And this is a simple table which represents a group which contains only three elements, 1 omega and omega square. And this concept can be extended if you consider the set of all fourth roots of unity under multiplication, that will form again a group, and that can again be represented using tabular form. Anyhow, uh, if you have such a tabular representation of a binary operation, then checking whether it is a group or not become much simple. And just observe the elements here. All the elements in the table belongs to the set 1 omega omega square, and therefore it is closed. Second property, associative property, being it is multiplication, associative property is obvious, so we don't have to prove that one. Then we are looking for the identity element. So when we multiply with 1, the column 1 omega omega square will repeat here, and therefore 1 is the identity element. Then inverse. To find out inverse of each and every element, or to check whether each and every element process an inverse or not, we need only to check whether each and every column and row process at least one or not. So if here is a 1, which means 1 has an inverse. Here we have a 1, which means omega has an inverse, which is omega square, and omega square has an inverse omega. So the columns corresponds to the entries of the columns which have the identity element as its entry corresponds to the inverses. So if we have a tabular representation for our structure, then checking whether it is a group or not is comparatively easy. Now, the next concept is abelian group. A group is said to be abelian if A star B is equal to B star A for all A, B belongs to the group. Uh, so if you consider the cross product of vectors A cross B is not equal to B cross A in general. So they are not abelian group, or they are not commutative operators. And for matrices A cross B not equal to B cross A in general, and therefore they are also not commutative. And the addition, multiplication, etc. depend on set of all real numbers and complex numbers are abelian, or they are commutative, and therefore they are said to form abelian groups. So anyhow, the concept of abelian group can be extended to abelian monoids also. If a monoid has this commutative property, then we say that it's an abelian monoid. Then we are going to define a new kind of addition and multiplication. They are known as addition modulo n and multiplication modulo n. Just go through the definition, and if it is not obvious, then just think it like this. If A and B are two integers, then the addition modulo m, A plus B mod m, is the remainder obtained when we divide A plus B with m. So we will illustrate it using a simple example. Consider the set of say 0, 1, 2, 3 and 4, Z4. Z4 is integers from 0 to 4, or the equivalence class modulo 4 are the elements of Z4. Equivalence class mod 4. We already had discussed about equivalence classes, and equivalence class mod 4 are equivalence classes 0, equivalence class 1, equivalence class 2, equivalence class 3, and equivalence class 4 is equal to equivalence class 0. So we just write down the representative members from here 0, 1, 2 and 3. And anyhow, we can use or we can write this Z4 in a different way. We can write it as 1, 2, 3, 4, 1, 2, 3, 4 and 5. This is equivalence class 4, not equivalence class 4. Okay, sorry, don't have 4 here. Equivalence class of 4 do not contain. Here it is up to 4 only. Okay, so Z4 can represent in these two different ways. Anyway, we are interested in the first representation. Z4 is 0, 1, 2 and 3. Then if we take two elements A and B from Z4, then the addition modulo 4 is the remainder obtained when we divide A plus B with 4. So we can, since here only we have a finite number of elements, we can represent this binary operation using a table, and it is like 1, 2, 3, 0, 1, 2 and 3. 0 plus 0, when we divide by 4, it is 0. 1 plus 0 is 1. 0 plus 2, 2 divided by 4, the remainder is 2. 0 plus 3, when we divide with 4, the remainder is 3. 1 plus 0, remainder is 1. 2 plus 0, the remainder is 2. 3 plus 0, the remainder is 3. Then 1 plus 1, 2. When we divide with 2, the remainder is 2. Then here it is 3. 3 plus 1, sorry, it is 1 plus 3. 1 plus 3 is 4, and when we divide with 4, the remainder is 0. 2 plus 1, 3. 2 plus 2, 4. When we divide with 4, the remainder is 0. 2 plus 3, 5. When we divide it with 4, it is remainder is 1. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6. When we divide with 4, the remainder is 2. So this will be the tabular representation of Z4. So in general, for any value of m, we can have a tabular representation of the binary operation. And anyhow, the identity element here 0, 1, 2, 3 repeats in a row corresponds to 0. So this is our identity element. So 0 is our identity element. And all the entities in our table is from Z4 and it is closed. So it have again it is addition and therefore it is associative. Now to check whether it has the what we call inverse, we check whether each and every column and row has the identity element or not. Here we have an identity element, which means the inverse of 0 is 0. Here again we have an identity element here. Therefore the inverse of 1 is 3 and inverse of 2 is 2 because here is our identity element, and here again we have the identity element. So the inverse of 3 is 1. So inverse of 1 is 3, inverse of 3 is 1, inverse of 0 is 0, inverse of 2 is 2. And for all elements in Z4 has an inverse, and there is an identity element. So we have all the 4 properties, and therefore Z4 together with addition modulo 4, actually this is the symbol, addition modulo 4 is a group. And if you observe this entities here, it is symmetric about the main diagonal axis. It is 0, 1, 2, 3, 0, 1, 2, 3, 1, 2, 3, 0, 1, 2, 3, 0, 2, 3, 0, 1, 2, 3, 0, 1, and 3, 0, 1, 2, 3, 0, 1, 2. So it is symmetric about the main diagonal axis, and that implies that this group is a commutative group. It is commutative, or in other words, abelian. It is abelian group or commutative group. So it's set for plus, or in general for any integer, positive integer m, the Zm is a commutative group. And the next example is the next concept is multiplication modulo m, which is almost same, but if you consider multiplication modulo m, then not every Zm become a group. Only Zm become a group when m is a prime number. So let us consider Z 5. Z5 together with multiplication modulo 5. So let us consider the entities. Sorry, here we don't consider Z5 star, which means we are eliminating 0. So what we have is 1, 2, 3, and 4. 1, 2, 3, and 4. Z5 has entities 0, 1, 2, 3, 4. And Z5 star has elements 1, 2, 3, and 4. It has only n minus 1 or 5 minus 1 equal to 4 elements. And 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4, 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6. But when we divide 6 by 5, the remainder is 1. 2 into 4 is 8. The remainder when we divide by 5 is 3. 3 into 1 is 3. 3 into 2. 3 into 2 is 6. 3 into 3 is 9. When we divide by 5, the remainder is 4. 3 into 4 is 12, and the remainder is 2. 4 into 1 is 4. 4 into 2 is 8. 4 into 3 is 12. And 4 into 4 is 16. The remainder obtained when we divide by 5 is 1. Now, that's the tabular representation of the binary operation multiplication modulo 5 on Z5 star. Now, if you look at the elements in the table, all the elements are from Z5 itself, and therefore it is closed. Then here corresponds to the element 1. The entities repeats 1, 2, 3, 4. So the identity element here is 1. So there exists identity element, and the identity element is 1. And to check whether it has an inverse for all of its elements, we check whether the identity element is present in each and every column or not. Here, 1 is present here, 1 is present here, here, and here. So each and every column and row has a 1, and therefore each and every element has an inverse. So inverse of 1 is 1, inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 4 under multiplication modulo 5. Now, this is the example for multiplication modulo 5, and we can change this 5 with any prime number, and it becomes a abelian group. It's an abelian group, obviously. But if we consider some Z6 star, what happens is, so the entities are 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And the elements in obtained is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 into 2, 4. 3 into 2 is 6. The remainder obtained when divided by 6 is 0. And the 0 is not belongs to Z6. 0 is not an element of Z6, and therefore this operation is not closed. It is not closed, and therefore is not even a semi-group, is not a monoid, is not a group. So this operation is not closed. Under multiplication modulo 6, which is defined on Z6 star, is not closed. So when we consider the addition modulo 5, addition modulo M, it is an abelian group under addition modulo M, but it forms Z star P form multiplication modulo P only when P is a prime number. If P is not a prime number, the operation defined multiplication modulo P is not closed, and therefore it will not form a group. That's the concept of addition modulo M and addition modulo N and multiplication modulo N. And these operations are very much important, and it has a lot of applications in computer science, and therefore that is important anyway. Then we have the concept of subgroup. Just go through the definition. If G is a group and H is a subset of G, and star is the operator defined on G, then if H star is a group under the same binary operation, then it is called a subgroup of G. So if you consider a set of all real numbers together with addition, then it is a group. Then we consider a subset of R. Say consider set of all rational numbers. Set of all rational numbers, and under addition, set of all rational numbers under addition is also a group. We restrict the same addition to the rational numbers. If we take two rational numbers like a by b and b c by d, their sum is again a rational number. Then the inverse of any rational number under addition is say a by b is a rational number, then its inverse is minus a by b, that's again a rational number. And the identity element of addition is 0, and 0 is again a rational number because 0 can be written as 0 by something, 0 by a, and that's a rational number. And therefore q plus is a group. This is a group, and this q plus is said to be a subgroup of r plus. So that's the concept of subgroup. And to prove that a particular subset h of g, a subset h of g, in order to prove that h is a subgroup of g, and if there is a binary operation star is defined on g, we need only to prove that a star b inverse belongs to h for all a comma b belongs to h. So that's a simple method by which we can prove that H is a subgroup. We can also prove by establishing all the four conditions of a group: closed, associative, existence of identity, existence of inverse. If we prove all those four conditions, then H becomes a subgroup. But instead of proving that, it is not necessary or not necessary to go through all those four conditions. We just have to prove that A star B inverse belongs to H. And if H is a finite set, then we don't have to go this further. Just prove that A star B belongs to H, or in other words, H is closed. If H is closed, then it becomes a subgroup. That happens when H is finite. If H is not finite, we just need to prove that A star B inverse belongs to H for all elements of A, for all A B belongs to H. And remember one thing, A and B are elements of H, and they are again elements of G, and therefore B being an element of G, it has an inverse. But the problem is whether the inverse belongs to H and whether A star B inverse belongs to H. Anyhow, there is an element A star B inverse in G, and our problem is to check whether that A star B inverse belongs to the subset H for all A and B. Now that's the concept of subgroup. And anyway, in a similar way, we can define the terms like monoid, submonoid, and sub semi group. All those definitions are valid. If you have a monoid M and N is a subset of M, and if you restrict the binary operation star defined on M to N, and if N star is a monoid, then it is known as a submonoid. And in a similar way, we can define the case of sub semi group also. Now, there are some important properties of uh, elements in a group as well as in monoid or semi-group. Okay, the properties are, first one is identity element is unique. So the identity element exists only when it is a monoid. So that property is not valid for a semi-group. But if in a semi-group, if there is an identity element, then it is unique. So we have to prove uh, these two or these three properties. First one, the identity element is unique. Our method is like this. If possible, let us suppose that E and E dash be identity elements. Then since E is the identity element and E dash is an arbitrary element, we can write E star E dash is equal to E dash star E is equal to E dash, because E dash is an arbitrary element of the group and E is the identity element of the group. Then, since if we consider E dash as the identity element and E as the arbitrary element, then E star E dash is equal to uh, E dash star E is equal to, here we consider E dash as the identity element and E as the arbitrary element. So it is equal to E. Then from these two identities, we can conclude that E dash is equal to E. So if there is two identity elements, then that will coincide. So there is only one identity element in a monoid as well as in a group. Now, if we have uh, a group and if we have an arbitrary element, say A be an arbitrary element, and then A has only one inverse in the group G. If it has an inverse at all, then it is unique. So let us assume that A belongs to G, a group, and let A dash and A2 dash be the inverses of A and inverse on that. So there are two inverses for A. Now, since A dash is an inverse of A, we have A dash star A is equal to A star A dash is equal to the identity element, and the identity element is unique. And since A2 dash is an inverse, A2 dash star A equal to A star A2 dash is equal to the identity element. So these are two equations, and we start with A dash. A dash is equal to A star E, and that's equal to A star, this A dash star E. So it is A dash star, here we have E is equal to A star A2 dash, A star A2 dash. Now we know that since it is a group, it has associative property. So it is A dash star A star A2 dash. That's equal to E star A2 dash, and that's equal to A2 dash. So what we get is A dash is equal to A2 dash. So if any element in G has an inverse, then they are the same. The inverse of an element is unique. And the next thing is, in a group, if AB is equal to AC, that implies B is equal to C, and BA is equal to CA, then B is equal to C. So the first one is right cancellation law and left cancellation law, and the proof is very simple. AB is equal to AC. Now we just pre-multiply the expression with A, the inverse of A. Since it is a group, A has an inverse. So A inverse AB is equal to A inverse AC. And since we have the associative property, we have A inverse into B is equal to A inverse into C by associative property. And since A inverse is E, it is E into B is equal to E into C, and E is the identity element, so we have B is equal to C. So that's the proof. So here we don't write the binary operation here, and if star is the binary operation, then we have to put the star. If dot is the binary operation, so we have to put the dot here to make it simple. In some cases, we eliminate the binary operation from our proofs. That is okay, but if there is the binary operation is not uh, if not making confusions, then it's okay. Otherwise, it's better to put the exact symbol in between elements. Okay, that's uh, three important properties of um, a group. Now, for the time being, we are just winding up here, and in our next classes, we will go through some more properties of groups, some more results regarding groups and subgroups, and a few more examples of groups and few more definitions related to groups and an important theorem which is known as Lagrange's theorem and some extensions of the concept of group, etc. So for the time being, thank you.